So hello everyone, my name is Sam Perry, and today I'm going to be talking about my implementation of characterizing possible failure modes in physics-informed neural networks, a paper previously done in 2021 by the authors listed above. That's the reference for them. But before we get started, I want to go into a brief overview of what this presentation will cover in the next 15 to 20 minutes. So first, we're going to start off with the introduction into partial differential equations, and then move into the background of the problem and pins in general. Next, we'll move into the paper's contributions and the methods that they use to conduct their experiments, and then we will end it with my implementation of the original paper, as well as a conclusion discussion surrounding the importance and future work of pins. So to get started, I'm just going to give a brief introductions. So partial differential equations, or PDEs, as they're commonly referred to and will be referred to throughout this paper, are mathematical equations that allow for the measurement and description of specific scientific phenomena. For example, PDEs can describe how one or more substance transforms into and diffuse throughout a specific space. Equations are largely based on governing laws of physics or chemistry, and they typically define many aspects of specific interactions within the universe. As such, these equations can be extremely complex, and even the simplest of equations can be quite computationally expensive to solve, and therefore a number of numerical techniques to solve these and approximate these exist, if they do exist. So the complexity of the equations typically, due to the complexity of the equations, they typically have to be approximated, and some numerical approximation techniques exist, as I said, but a more common and modern approach for solving these PDEs is to add an element of machine learning to aid in finding these solutions and then expand upon them. Typically, this comes in the form of neural PDEs, where they use a neural network and apply some underlying domain knowledge specific to the scientific discovery that is common within the PDE, and sort of guide the neural PDE to the correct approximation. So, as I've said, PDE methods and I've been over PDE methods, and that's going to be discussed further in this method, but some of them come in the form of physics-informed neural networks, commonly referred to as PINs. PINs work, they allow researchers to incorporate some previously discovered domain knowledge as constraints to the loss function of the neural network. Traditional machine learning optimization techniques can then be used and to optimize this loss function, and this makes PINs a very promising technology that allows domain knowledge to be applied and used by the neural networks before training even begins. There's been promise shown in previous PIN research, and PINs can be extremely difficult to work with due to complexity and application of these domain-specific PDE constraints that we'll talk about later on. And typically this leads to different failure modes during training, which are difficult to diagnose and resolve, making PINs very difficult to manage when modeling a system or an interaction with PDEs. Next, we're just going to go into the background of failure modes and PINs and how constraints are added to neural networks to create a PIN. So again, PINs are promising technologies that have been known to fail to model complex PDEs. And this paper proves that it is mainly due to there's no way to it's mainly due to the way the loss function is constrained in more traditional PDEs. So the general form of how constraints are made in the loss function is shown in that equation right below the slide, or in the middle of the slide, where f is some operator that represents the PDE. U of x of t is the perimeter or the parameter of interest, and x and t represent space and time, and they cover the entirety of the spatial and temporal dimension for the problem that we're going to be covering. Some common examples of the F operator that models or that represents the PDE is convection equations, which will be tested later on, diffusion equations, and the Laplace equation. And the choice for these depend on the problem and how the PDE and how the loss, and they affect how the loss function is effectively constrained. Now, there are two main ways that a constraint can be imposed on a loss function, either through a hard or a soft constraint of the neural network during training. in the loss function. So a hard constraint constrains a loss function. It's shown on the left. And what it does is it selects the solution such that the constraint is fully solved. So the operator is set equal to 0 at a certain state. Thus, we fully define the PDE that we have in place for the pin for the loss function. Now, in practice, this is not practical because it's nearly impossible to derive a fit for the data given the hard constraint in the loss function. So instead of clearly defining these values with hard constraints, we typically use soft constraints in pins. So the optimization function for a soft constraint is shown directly below on the right. So what this does is instead of directly defining the values of the PDE, it sort of introduces this regularization parameter, the lambda of f, and that defines how heavily weighted the PDE-based residual will be during the training. So how heavily reliant on the PDE we are for training and like learning. During training, so it encourages the model to learn the values rather than just explicitly requiring them to be on the model. Now with soft constraining, as the optimization just penalizes any violations of the PDE, wherever u is not equal to 0, basically, then there are some possibilities that the model can be incorrect and inaccurate. As I just previously stated, these constraints act as sort of a guide to the neural network given the prior knowledge that we were trying to implement. So there's no guarantee that the model will follow the laws of the domain knowledge with the soft constraint. What the soft constraint does is it is going to approximately satisfy these constraints, and there is no guarantee that the constraints have been fully satisfied with the model when it is completed training. This can lead to highly incorrect or even false models that sort of violate the governing laws. So if you think of, for example, the law of conservation of energy, if a model only slightly approximates the constraints of the PDEs that surround the law of conservation of energy, then there's a chance that it could violate the full law and therefore violate the physics and the laws of physics of the domain that we are currently studying. Now that we have a background in depends and constraining loss functions, I'm going to talk about sort of the contributions and the methods that the paper used to create these solutions that it's going to pose. So the authors made several contributions to pin research throughout the paper, but first they analyzed and diagnosed some major problems with traditional pins, so the failure modes of pins. These traditional pin approaches only worked with PDEs that have relatively small coefficients or simple parameters. So when they fail when the problems become more complex or with larger coefficients and more parameters, which is very, very common in PDEs that define our environment and in interactions with like chemicals or anything like that. So they analyzed the loss landscape of these pin models that were trained. And additionally, they find that the ones with the larger regularization parameters, so the lambda of f and the soft constraint, are often harder to optimize than the ones with the smaller regularization parameters. But this does come at a cost because the larger the regularization parameter, generally the more accurate and higher performing it is. Secondly, the authors posed two separate solutions to aid in the optimization and to fix the failure modes of the observed pins. First solution that they offered is called curriculum regularization, which allows the model to learn PDEs with larger coefficients by first learning PDEs with smaller coefficients. Or learning the same PDEs with smaller coefficients, basically. It's very similar to curriculum learning in other deep learning experiments, where the model first trains on smaller, easier to learn data sets, easier to learn coefficients, and then these coefficients are gradually increased to be more complex during the training step, with the ultimate goal of curriculum regulation being that the model has gradually learned the constraints rather than putting the final constraint on the model from the beginning, allowing it to learn the laws and the models of the scientific domain as it grows, basically as it learns. Now, the second solution for fixing failure modes in pins is to treat training as a sequence-to-sequence task, rather than just giving the model all the data from the beginning over the entire temporal dimension. We give it the beginning segment of the data and then slowly increase. Once it's learned the beginning segment, we give it the next segment. So the second segment sort of relies on the first segment. What this does is it allows the model to learn the constraints over a much smaller time domain and then apply this to other segments from the next set of data. So this helps it sort of break down the problem into a smaller, sort of break down the really complex problem into a smaller set, and then learn, I guess, in a smaller way. So for the architecture, to implement models and solutions, the authors kept the architecture of the models consistent throughout, using a 6-layer fully connected neural network consisting of an input layer, 4 hidden layers, and then an output layer. And the input layer depends heavily on the model being tested, but the input to the model was the sample data from the equations that the models were attempting to learn in both the spatial and temporal, or X and T domain. The first layer is fully connected to the first hidden layer, which is a 50 neuron layer using a hyperbolic tangent activation function, or TANH as it's more commonly referred to, for each neuron. The authors didn't explain their choice for this activation function, but from other research and other pen investigation, it can be assumed that they chose the TANH function due to its popularity and relative simplicity, as opposed to some other activation functions that can be used, but they didn't really give a specific reason. And then the first hidden layer is then fully connected to the next hidden layer in the architecture. And it's important to note here that all hidden layers are completely identical, fully connected 50 neurons with the same activation functions. Now, the last hidden layer is connected to an output layer, which is just a single neuron that outputs the model's final prediction for the state value that it is given. So for optimization, for every model that they tested, they had a periodic boundary condition placed on the model to help learn the fundamental domain and sort of fundamental domain knowledge easier around creating a boundary of a sort of exploration and defining the boundaries more clearly. They added this term to the loss function to further define the domain, making it easier for the model to learn the coefficients, basically. It is interesting to note, though, that the authors used the limited memory BFGS, or LBFGS optimizer for all models, and they found that through testing and other research that LBFGS typically performs better for traditional pins over other standard stochastic gradient descent methods that are common in many other problems. It's just an interesting take that the LBFGS is the best optimizer for pins in general. So now we're going to move on to the experiments phase and what they did. So in the experiments phase of the project, the authors varied the convection, reaction, and diffusion coefficients. So these are 3 separate coefficients. And they did this over 2 tests. The first test, they tried to get the model to learn just the convection coefficients of a simple equation. And then they tried to get the model to learn the reaction diffusion coefficients, which is 2 coefficients of another standard PDE. For each experiment, they ran about 10 models, and they took the average for the specific type of test they were running, which helped to analyze the solutions and diagnose the problems more easily and see the failure modes more easily. So the first experiment they considered is a one-dimensional convection problem, which is a hyperbolic PDE. This is most commonly, or one of the most commonly found model transport phenomena. It's shown below in that long equation. But the important part is the beta there, right next to the du over dx. So this is the actual convection coefficient that the model is attempting to learn and then model. They additionally, mention they applied boundary conditions to all of these, to the loss functions, which are shown below. And then the loss function is also shown at the very bottom, which is what they were trying to optimize with the model. Pretty complex, but the other experiments get more complex. Speaking of the next experiments, they considered a 2-dimensional problem where there's a reaction diffusion system and there's 2 coefficients in a single PDE. To the right is the reaction diffusion system that the model is trying to study. So nu, or the v, is right next to the v delta squared u over dx squared. That is the diffusion coefficient. And then to the right of that is the rho, or reaction coefficient. And the model was attempting to learn both of these. Additionally, the model had some boundary conditions that were applied in the loss function. But in general, the loss function for this problem is shown at the very bottom, and it's much more complex and much harder to learn than the previous loss function, making it just an all in all a more complex problem that the model is attempting to learn. So next I'm going to talk about my implementation and how I got the model and paper to work. So obviously I went on Papers with Code and found the open source project that the authors posted and its GitHub link, which is right there at the top. It's open source, so it's pretty easy to access and use. On the right, you can see the possible arguments that can be passed to the model during training and before training. This makes it really highly customizable and pretty easy to implement and edit as you would see fit or as you want to test anything. And as far as what I did, I replicated the paper and the results. And I also compared some of the traditional models that were tested on the more complex coefficients to lower coefficients with traditional models, as the paper didn't really, they just mentioned that traditional models fail at larger coefficients and then succeed on lower ones, but they didn't really implement any lower coefficients. So I tried to do that to sort of model that myself and visualize just how much of a discrepancy there is between more complex coefficients and their lower counterparts. Okay, so for the first experiment, recall that the higher the beta and the convection, higher the beta or the convection variable for the PDE, the more complex of a coefficient it is. So to begin with, I wanted to test on a traditional pin with a relatively easy coefficient. And as you can see with the beta of 1, the model learns the distribution pretty well and is really able to replicate and predict data accurately. It had very small relative error and absolute error, and just in general performed pretty well. They look pretty similar. This is in comparison to the RAN model that ran on the beta of 30, which is much more complex version of the model, obviously. So with the traditional pin, as you can see on the left, the correct distribution of data, it's supposed to be those nice solid rows of color. And on the right is what our model predicted. So you can see the boundary conditions are pretty well modeled due to the fact that we've predefined those. We have given them more information around the boundary conditions rather than just sort of anywhere else. But you can also see that the relative error and absolute error are very high and almost 2 to 3 orders of magnitude larger than the solution for the lower beta, meaning that traditional pins do not perform well on complex or very complex coefficients or models based on PDEs. So the next experiment was much more difficult to implement, as some of the customizations that need to be made for this model are not as readily available or just accessible to a programmer. But this is testing the reaction diffusion from the original pin. And as you can see in the correct distribution of data on the left, that there's a little bit of higher level of action, a little bit of different color changing around the 0.3 mark, which is not caught at all by our model that was predicting the reaction diffusion solution with the original traditional pin. So obviously the relative and absolute error are extremely high for this model as well, and as such it doesn't perform well at all. So now this is the learning convection curriculum, or learning convection with curricular regularization. This is the paper implementation of the curriculum regularization. And as you can see, it models the first data quite well. I will go back to that. So you can see on the top left, that's the original. And now this is what my model has predicted as the outcome. It learns it much better than with much higher accuracy than the original and the traditional pin, or than the traditional pin, meaning that the model with curriculum regularization are much easier to learn the complex distributions of data. Now this one, I couldn't get a great picture from my implementation, so I'm going to use the picture from the paper to sort of demonstrate the point of sequence-to-sequence learning. When you pose the reaction diffusion problem as a sequence-to-sequence test rather than just giving all the data to the model itself, it learns the solution much better than previously. On the left is the exact solution. On the right is sort of what you see is what our model, or the pin with sequence-to-sequence task, posing it as a sequence-to-sequence task. That's what our pin has predicted. And in the middle is what a traditional pin would have predicted for this problem. So you can see that the traditional pin is not very accurate to the distribution we see, and the sequence-to-sequence task pin is much, much better. And now finally, to wrap it all up, I want to discuss the results of the paper mean and what the results of the paper mean, and also the conclusion. So with all that being said, pins are obviously a very promising approach, and they can help us expand in a more scientific areas or scientific niches than previously done before with machine learning. Pins in general struggle with more complex problems, so we need to sort of address these failure modes as they come up and diagnose them to create the best model for working with specific PDEs that are more complex or more in complex environments. Additionally, I just want to point out that approaches that the authors use are pretty intuitive. If you think of like teaching a child, you wouldn't want to start off with the easiest things first. You would want to start off with the easiest things first and then slowly build on those foundations and basics until they can learn more complex things. And this is what the authors did with curriculum memorization, or if you didn't want to teach them everything at once, sort of allow them to learn over time. And some of these really more intuitive approaches can be used, I believe, to combine neural networks and machine learning. And our scientific domain knowledge that we have to sort of increase the outcome and the performance of pins. Finally, obviously the paper does have two solutions that in theory and a little bit of testing work, but more development testing is needed to sort of solve all the major problems with pins. The paper only implemented two pretty relatively simple or common PDEs, and they aren't the most complex in comparison to other interactions with systems and other variables or PDEs that have multiple coefficients. So I think more development and testing is needed to sort of solve these failure modes and address some more points of contentions when pins do perform very poorly. But there is going to be, or there is, with these approaches, there is a great increase in accuracy and performance of traditional pins in comparison to on more highly complex PDEs and constraints. And with all that, thank you for your time. I'm done.